I'm your anchor, Jaren Canary, and today we're going to be discussing Lab 5, where we investigate an important concept in electrical circuits known as Kirchhoff rules. Principles that help scientists and engineers understand how electricity moves through complex circuits. These rules are based on two fundamental laws of physics, the conservation of energy and the conservation of charge. According to Kirchhoff's junction rule, the total current entering a junction must equal the total current leaving the junction. The loop rule states that the sum of all voltage changes around a closed loop in a circuit must equal 0. These principles are widely used in real-world technology such as electronics, power grids, and computer circuit boards, where engineers must carefully control how electrical energy flows through multiple components. To learn more, we're joined by our lab scientists who helped conduct this experiment. Can you introduce yourself and explain what the objective of the experiment was?
Howdy, my name is Hannah Macias, and I am your local scientist. Absolutely, I would love to tell you more about this. In this experiment, our objective was to test Kirchhoff's junction rule and loop rule experimentally. By measuring the current and voltage across multiple resistors in a circuit, we could compare our measurements to what Kirchhoff rules predict and determine how closely real circuits follow these theoretical laws.
We're doing materials now. Okay. Before conducting the experiment, what materials did you and your team use?
So, we got together voltage current sensors, current wires, the PASCO universal interface and capstone programs, resistors, and those were really it that we used, but let me go into more detailed definitions. So, what is a voltage current sensor? This is a device measures the voltage across components and current flow through the circuit. Now, the current wires, these are connected to the component and allows electricity to flow through the circuit. Now, the PASCO, which I keep calling PASCO, universal interface, this device connects the sensors to computer and allows us to record measurements digitally. Now, we go into the program that we use, which is Capstone. I think we're all very familiar with that. This software collects and displays the voltage current measurements in real time. Also, we had the resistors. The component limit the flow of currents in the circuit and create measurable voltage drops. So, on the actual resistors, we labeled that R1 through R4, so we could just keep track of what was where, because sometimes it can get a little confusing. So, try to be as organized as possible.
Thank you. Let's take a look at how the experiment was performed in the lab.
Cut to these photos. First, we labeled each resistor from R1 to R4 using tape so we could easily identify them during the experiment. Step 2. We measured the resistance of each resistor using a multimeter and recorded the values. Next is number 3. After that, we assembled the circuits using the resistor wires and the PASCO universal interface according to the circuits diagram that was drawn on the board by our lovely TA. 4. In the Capstone program, we set the signal generator to the direct current at 7 volts with voltage limits of 10 volts and the current limit of... Oh, sorry. This is 1.
That's 1? Okay. This is 2. This is 3. Because I think they're supposed to be like...
No, I'm looking at this right now.
So I mean, it's like R3, R2, R3 together. So maybe R1 is supposed to be like...
Oh, I see what you're doing.
See what I mean?
Yeah.
And then like,
4.
you have to attach 4.
And that's on negative, right?
Positive.
No, R2 is negative.
R2 is negative.
Okay, then yeah.
And then R1 voltage is...
And the voltage sensor wires on R1. So...
Yeah, that's this. Wait, no.
See what I mean? They're saying that both need to be on R1. And then the black current goes to R4.
Okay, red current on top. Okay, red current is on top of R2.
Yes.
Right here.
R2 one,
We place the current sensor onto the circuit to measure current through each resistor, while the voltage sensor measured and the voltage drop across each resistor. Finally, we ran the circuits and recording the voltage and current values for resistors R1, R2, R3, and R4.
Thank you.
Just on R2? Or is it down here? It'll be up here? Or is it here? Because last time, remember when we had 4 over here?
I think it might be this way, and then we have this one here.
Oh, there we go.
Chat, that's a bogey.
Should I stop it?
Yes.
Oh, I'm stupid.
It happened to me. It happens. We chill. There you go. Don't worry about it, dog. Or you. Yeah, I think we're gonna roll now. Scratch that up. Red current. This is supposed to be here. This is black current on R4. That's how it's supposed to be.
Yes.
Sensor wires on R3. So it says current's supposed to be here. And then we need this one, I believe, here. And then the voltage sensor wires are on R3, which is on the negative, so it should be, I'm assuming here. Let's give it a shot. That's my choice. I mean, it should be pretty simple because he said R2 or 3 was going to come up.
That's on top of that's right.
That's 2.
That's right.
Yeah.
Oh, so it should be
Here.
red current junction R1 R2.
This is 2 and this is, or no, this is
1 and 2, and then this is 3.
Okay.
So R1 R2,
Yeah.
and then black current on negative voltage sensor.
Yeah.
And then we take these two and we put them both on R4.
That's it. More than we change. It will change.
Now let's look at the data collected from the experiment.
Alrighty. So, we measured the voltages and currents across each resistor in the circuit. And our recorded voltages were R1 is equal to negative 9.68, R2 negative 4.92, R3 negative 4.92, and R4 is negative 4.88. Our measured currents were R1 is equal to negative 12.254, R2 negative 2.131, R3 negative 2.131, and R4 negative 13.273. To test Kirchhoff's junction rule, we compared the current through R4 with the sum of the currents through R1 and R3. The equation was R1 plus R3 is equal to our R4. Our values were for R4 negative 12.273, and the sum of R1 and R3 is negative 14.385. This resulted in a percentage difference of about 8.3, showing the measurement values were relatively close. Next, we tested Kirchhoff's loop rule. For the first loop, we used the equation VE is equal to R1 plus R plus VR4. Our results showed a 0% difference, meaning the measurements voltage matched the exact values. For the second loop we tested, VR1 is equal to VR2 plus VR3. So VR1 was equal to negative 9.68 and VR2 plus VR3 gave us negative 9.84. This resulted in a percentage difference of about 1.65, which is very close. Therefore, it supports the loop rule.
Thank you. discussing the conclusion and then the conclusion questions. Okay, so to wrap up our investigation, what did your team ultimately learn from this experiment?
So, this experiment tested Kirchhoff's junction rule and loop rule in an electrical current containing 4 resistors. The current was connected to a 7-volt direct current source, and sensors were used to measure the voltages across the resistor and the current flowing through them. The measured values were then compared using Kirchhoff's equation to see if the currents at junction and the voltages around a loop followed the expectations and the relationships. The results showed that the sum of the currents and voltages were pretty close to our theoretical predictions, with some small percentages that were different. To give an example, about 8.3 for the junction rule and 0 to 1.65 for the loop rule. These small differences are likely caused by factors such as resistor tolerance, measurement uncertainty, or minor connective issues. Overall, the experiment confirmed that Kirchhoff's rule accurately describes how currents and voltages behave in electrical circuits.
So I do have a couple questions for you. So first, what did this experiment reveal about Kirchhoff's rules?
Good question.
Thank you.
The experiment showed strong agreement with Kirchhoff's theoretical predictions. Our results demonstrated that, as we spoke before, the total current entering and leaving the junction was approximately equal. The sum of the voltages around the closed loop in the circuits was very close, but not 0. So the percentage differences were small, especially for the loop rule, where one loop showed 0% difference. Some small differences did occur, and these could have been caused to, again, resistor tolerance, small measurement errors in sensors, or loose or imperfect wire connections.
I see. So is it possible to create another loop in the circuit?
Of course. Because the circuit contains multiple paths, we can draw additional closed loops and apply Kirchhoff's loop rule to basically all of them.
I see. Could these differences be minimized?
Yes. We could reduce error by, I guess, ensuring all connections are secure. Use more precise resistors,
I see.
and carefully calibrate measurements and equipment. Yes, we did it to the best of our abilities, but we can always get better tech. Even with these small differences, though, our results confirm Kirchhoff's rule accurately describe how electrical circuits behave.
Thank you. Before we finish today's report, we'd like to recognize the team behind this experiment. My name is Jaren Canary. I was your anchor and journalist, and I helped with the on-screen presentation and helped collect the data and helped write the script.
So, hi, I'm Hannah. I'm Hannah Macias. I am your local scientist. I participate in a lab and in this video, and we'll also mention Remington participated in the lab and helped with data. Damien participated in the lab and helped with data. Adam edited the video and participated in the lab.
Thank you for joining us.